Okay, so we're going to start going into the Bohr model, but before we go into the Bohr model, you actually have to understand light. And so light is consisted of particles called photons that act like a wave. So the first thing we're going to talk about is when the Bohr model was discovered, the way it was discovered was how light was emitted when certain atoms were excited. And so we kind of need a background on waves before discussing the Bohr model. Okay, so let's talk about waves. So this is your wave. We call it a transverse wave. There's several parts of the wave we need to know. The first is a wavelength. So the wavelength is known as lambda. So lambda is the symbol for wavelength, and it's the distance, usually we say from like the crest to crest or trough to trough. This is what's known as the wavelength. And it's measured in meters because it's a length. Frequency is the next thing. And so it's the number of wave cycles over a second. So it's the number of waves per second. And then we measure it, just like we measure wavelength in meters, we measure these cycles or frequency in Hertz. Hertz is also known as s to the minus 1. S to the minus 1 is known as 1 per second, right? So it's the number of cycles per second. So this is per second. And so here you have frequency. Here you'll see this is low frequency, medium frequency, and high frequency. All right. Now, what is the speed that these waves travel at? So these waves travel at a particular speed, and that speed is the speed of light. So all electromagnetic waves, we'll talk about electromagnetic waves later, but all these waves that we're talking about that have energy travel at the speed of light. The speed of light is 3.00 times 10 to the 8th meters per second. This is a constant. And so when you multiply the wavelength by the frequency, you get the speed of light. We're going to talk about this later, but this means that the speed of light, which is a constant c, so the speed of light is c. So c equals the wavelength, multiply the wavelength by the frequency, so the wavelength is lambda times v, which is the frequency. This is not v, it's nu, which is a Greek letter. So one more time, speed of light, c, equals wavelength times frequency. And c is what we call a constant. This is always the speed of light. And the speed of light is always 3.00 times 10 to the 8th meters per second. Oh, there it is. All right, so let's talk about the relationship between frequency and wavelength. So as you can see here, here's low frequency. You have not many waves per second, so here's low frequency. So what I want you to notice is when it's low frequency, the wavelength is longer, and then when it's high frequency, the wavelength, it looks like it almost compresses, right? So here's one wavelength, here's another wavelength, and you'll notice as frequency increases, wavelength decreases. As frequency decreases, wavelength increases. We call that an inverse relationship. When one goes up, the other goes down. So I think it says it right here. As wavelength increases, frequency decreases. As wavelength decreases, frequency increases. What about the relationship between wavelength and energy? So we have to think also that frequency, a higher frequency equals a higher energy. So frequency and energy are related directly, meaning one goes up, the other one goes up. So as the energy increases of a wave, the frequency increases. Well, what happens to the wavelength? Well, the wavelength will therefore decrease. So let me write that down for you. So as energy increases, this increases the frequency. And remember, frequency decreases wavelength, so it decreases wavelength. And then so as energy decreases, the frequency decreases. And so therefore the wavelength increases. Okay? So as the wavelength increases, the energy decreases. As wavelength decreases, energy increases. All right, so here I just showed you how to solve these type of equations. So here's your equation. So it says, let's do the example together. What is the frequency of an X-ray that has a wavelength of 5.11 times 10 to the minus 9th meters? So the speed of light equals the wavelength times the frequency. The speed of light is always 3.00 times 10 to the 8th meter per second times or equals the wavelength, which is what we have. We have it. It's right there. 5.11 times 10 to the minus 9th meters times the frequency. So frequency is what we're trying to figure out. We divide both sides. 5.11 times 10 to the minus 9th meters over 5.11 times 10 meter, right? So therefore our frequency equals so 3 so you should have got, now this has 3 sig figs. This has 3, so your answer should have 3. So my final answer should be 5.87 times 10 to the 16th. This is frequency, so frequencies in hertz, right? Okay? Cool. All right. So now we're going to go into the electromagnetic spectrum. You might have heard the electromagnetic spectrum earlier. The electromagnetic spectrum are all the waves that travel at the speed of light. They possess energy. So the part of the electromagnetic spectrum we can see is called the visible part. So 10 to the minus 6 meters is around where the visible part we can see. So it's right around here is the visible spectrum. If you increase the frequency or energy, you get higher energy waves. So you'll see the frequency increases as we go this way, right? And so you can even get to gamma rays, which have really high frequencies, low wavelength. So this is the higher energy. So these are waves obviously we can't see, but they have high energy. We worry about them, so we protect ourselves against X-rays, UV rays. And then if it goes this way, this is lower energy. And so we don't worry about protecting ourselves against these low energy waves, but they have really long wavelengths. So like radio waves have really long wavelengths, and so we can use them for like radio waves to like transmit information, that kind of stuff. What I want to focus on is the visible spectrum. So the visible spectrum is what we can see, and so that's the part we want to talk about. You might remember there is a acronym, Roy G. Biv. So red, orange, yellow, green, blue, indigo, and violet. And so here, this is the spectrum that we can see. If you follow this, excuse me, red has lower energy, and so therefore a lower frequency and higher wavelength. Violet has higher energy, and therefore it is a lower wavelength and a higher frequency. Okay. All right, so we talk about light. Light is one of the parts of the electromagnetic spectrum. Like we talk gamma rays all the way to radio waves. Light is the visible part that we can see with our eyes. And so what's the relationship between wavelength and color? So we just kind of talked about this. We said that the red side is lower energy, and then the violet is higher energy over here. So remember, higher energy is lower wavelengths. And you can kind of see it, right? So right here we have a long wavelength, that's towards the red side, and here we have a short wavelength, and that's the violet side. So the longer the wavelength, the more red the color. The shorter the wavelength, the more violet the color. Remember, violet is higher energy, so shorter wavelength, higher frequency. Here's some homework you can work on, and then the key I think I posted, oh, actually there's no key. These are just 2 examples of practice that you can work on.